And number 6, find the relative x and min points using the first derivative test. And our function is 2x squared over x minus 1 quantity squared. So in order to use the first derivative test, we first have to find the critical points. So to do the derivative of this, we need to do the quotient rule. And within the quotient rule, this down here is going to need the chain rule. So we have the bottom times the derivative of the top minus the top times the derivative of the bottom. And this is where our chain comes in. So this is our u. So it's 2u to the 1 times our derivative of u. Well, in this case, that's just 1. So it's not really going to affect us, but you just want to make sure that you are always remembering that chain over the bottom squared. Well, it was already squared, so it's like squared squared, which will take us to the 4th. Now, remember, you're setting this equal to 0. So technically, you don't really care about the bottom, because the bottom is going to multiply with the 0 and just become a 0. So let's look at our numerator. We've got x minus 1 squared times 4x. Then we've got a 2x squared times a 2 and an x minus 1. So let me kind of clean this up a little bit, and let me show you what you can do to make things easier. 2x times 2 is 4x squared times an x minus 1. And let's all keep it over our x minus 1, and that'll be raised to the 4th, because the 2 minus 2 is to the 4th. Now let me show you what's going to make things easier for you. You could FOIL this, and then you could distribute that, and then you could distribute that, and you can combine all your like terms. What I typically like to do instead is I typically like to notice that I have an x minus 1 in both of these, kind of like a GCF, and it's going to cancel with the denominator. So I'm going to pull that out. And I'm left with 4x times the x minus 1, and then minus the 4x squared. But that x minus 1 is gone. Because what that does is that allows me to cancel this and make this a third. Now that helps me out a ton, because now I don't have to FOIL, I just have to distribute. I get 4x squared minus 4x minus 4x squared over x minus 1 cubed. Those 4x squareds are gone, and I'm left with just a negative 4x over x minus 1 cubed that I'm setting equal to 0. Okay, well that's just negative 4x equals 0 and x equals 0. That's my critical point. Now don't forget that x equals 1 is also critical. So you've got a 0 and a 1 being critical, because the denominator equaling 1 is going to make that 0. Now this one's critical stationary. The 1 is just plain old critical. Now we're using the first derivative test. So I can save a little paper. I'm going to do the first derivative test right here with a 0 and a 1. So a 0 is going to give me a 0, a 1 is undefined, but I still need to check both sides of it. Now, where is my highlighter? My first derivative is right here. Okay? That whole thing is the first derivative. So notice that as I plug things in, look at the bottom. The bottom is x minus 1, and then you're going to cube it, which means if that's a negative and then you cube it, it's going to stay negative. If it's a positive and you cube it, then it's going to stay a positive. So let's take a look at what goes on. If we plug in a negative 1, the top is going to be positive. The bottom is going to be negative. Well, a positive over a negative is a negative value. Okay? Now I need to plug in like a half, a positive half. So the top is going to be negative. The bottom is also going to be negative, because a half minus 1 is a negative value. But a negative over a negative means that I've got a positive. So right here, I already see that I have a relative min, because I'm decreasing, then I'm increasing. I have a relative min right here. Okay? Now let's look at the other side of 1. If I plug in a positive 2, that's a negative over a positive. Well, a negative over a positive is a negative. So here we this is an increasing and then decreasing, you have your relative max. So Interestingly, someplace where it was undefined, you actually do have a relative max. So that's why it's super important that you check these things. Now, the first derivative test means we need to check using the first derivative. So that's what we just did. So we find out that x equals 0, we said was a relative min. Whoops. And the reason it was a relative min is because the first derivative changed from negative to positive. X equals 1 is a relative max because the first derivative changed from a positive to a negative. Okay? All right, so I'll pull this down a little bit so you can see the top. You can go ahead and hit pause now if you want to. Copy all that down. And then your final answer right here, 0 relative min, 1 relative max. So that took care of number 6. Let's go ahead and look at number 7. I think I can squeeze it in on the bottom of this page right here. So number 7, it says, use the second derivative test to determine if you have a relative max or a relative min. All right, so the first thing you got to do is find your derivatives. So you have 3x squared minus 12. You want to set that equal to 0. Let's focus. There we go. We have 3x squared equals 12, x squared equals 4, x equals plus or minus 2. Please do not forget the plus or minus. We've already now talked about this a couple of times. Our second derivative is then 6x. Okay? That's all you have to do. We don't have to find our possible inflection points because we didn't ask for concavity or inflection points. We asked for relative mins and relative max. Now, it says to use the second derivative test, which means I'm going to plug in these actual values into the second derivative in order to find out if they're positive or negative. Okay? Basically, I'm going to find out the concavity at those 2 points. So if I plug in a negative 2, well, that's a negative 12, which means that right there I'm concave down. Concave down looks like this, which means I have a relative max. If I plug a positive 2 in, I get a positive 12. Well, positive means that I'm concave up. Well, that means I have a relative min, because it's down here and this one's right up here. So, to conclude, x equals negative 2 is going to be a relative max because your second derivative is less than 0. Because we use the second derivative test, right? And x equals 2 is a relative min because your second derivative is greater than 0. So we found a relative min and we were asked to use the second derivative test. And, oh, I was about to ask if there are any questions, but you aren't there. See, it's just like ingrained in my head. If you do have any questions, feel free to send me an email. All right, let's look at number 8. Number 8, they gave you a table. And I'm just going to draw the table real quick because I want to make sure that we can write on it, and I don't want to write on my worksheet. So the 0 is 0. I have a plus, a minus. I have a 0 and a 0. I have a minus, a plus, and a minus. All right, so things we need to know. So this first derivative is going to tell you where things are increasing or decreasing. The second derivative is going to tell you where you're concave up or concave down. Okay? So on this row, we know we're increasing, and then we decrease. On this row, we know we're concave down, we're concave up, and we're concave down. Okay? So those are some pieces of information. Now remember, I didn't give you a restricted domain, which means this thing is going from negative infinity to positive infinity. So these are all the numbers that you're going to be using in your answer. Now, the first thing they wanted was intervals of increasing. Well, we're increasing right here and right here, all the way to this 7. So we're going to increase from negative infinity to 7. Now on the quiz it's not going to ask you why, but on the test it is, so we need to say why. The reason, so if we're justifying our answer, is because the first derivative is greater than 0. You can't say the first derivative is a plus sign. You can't say that it was graphed on top. Okay, you need to use mathematical terms because you're going to want to sound smart when you're taking that AP exam. So you're going to say the first derivative is greater than 0. Now you could say the first derivative is positive. Don't just say first derivative plus sign. That's not going to work out. Greater than 0 or is positive. Those two things would work. Now we're decreasing right here where it's negative, and it's negative from 7 to infinity. Notice I have parentheses, not brackets. Make sure you have parentheses. And our reason is because the first derivative is less than 0. Now, next, I'm going to go ahead and do relative max and min, just because those deal with our first derivative of increasing and decreasing. So, a relative max. First, let's think about when and how we know. A relative max is when the first derivative changes from positive, to negative. A relative min is when the first derivative changes from negative to positive, and we could even put a little s right there. Right? So, if you're looking for a relative max, changing from positive to negative, well, look at your list. You've got a positive, positive, negative. That means this one right here changes from a positive to a negative. So x equals 7 is going to be your relative max, and you already have your justification because the first derivative changed from positive to negative. Now we need to look for when the first derivative changes from negative to positive. Well, we don't have one. Positive, positive, negative, it doesn't ever change negative to positive. So we write none. Please do not write 0. 0 is a number. The next thing I want to do is find my inflection points. Now, inflection points are where you change concavity. So where the second derivative changes signs. Now, I don't care which direction it changes the signs in, I just care that it changes signs. So we go negative, positive, negative. So we changed signs right here at x equals 3, and we changed signs right here at x equals 5. Now notice I can write them in a list, but please do not put parentheses around them. Parentheses around them would imply that you're going from an interval, or you're talking about a point. Well, we're not talking about a point, we're talking about two different points. So x equals 3 and 5 with no parentheses. The reason is because the second derivative changes signs. So now we can do our intervals of concave up and our intervals of concave down. Concave up is where you have your plus sign and your second derivative, so that's from 3 to 5. Again, notice parentheses, no brackets. And the reason is because your second derivative was positive or greater than 0. You will be concave down where the second derivative is negative, so negative infinity to 3, and then again from 5 to infinity, and that is because the second derivative is less than 0. So that is all the pieces of information you need to answer on number 8. So let's go ahead and look at number 9. Number 9, I gave you a derivative graph, which again I'm going to draw in here so that I can go ahead and write on it. So I've got a point right here, a point right here, a point right here, a point right here, a point right there. And our graph looks something like that. There we go. And it says first derivative. Okay, now we have all of our justifications. So all of our justifications are going to be the same. So I'm not going to rewrite my justifications, but I'll refer back to them. All right, so intervals of increasing. That's where the first derivative is positive. Well, our first derivative is positive here on top. Okay, now again, you can't say justification is on top. On top doesn't work. You have to say because the first derivative is greater than 0, the first derivative is positive. But in this case of our graph, we're going from -3 to -1. Okay? Now again, our justification is the same as it is right here, because the first derivative is greater than 0. All right, let's look at our decreasing. Our decreasing is going to be when the first derivative is less than 0. So the same as this right here. When we're less than 0, or we're on the bottom, in those areas right there. So in this case, it'll be from -infinity to -3. And then again, from -1 all the way to infinity. And the justification is because the first derivative is less than 0. Okay, our relative max. Now, for relative max, we're looking for when the first derivative is positive and then negative. So it's on top, and then it's on the bottom. So the first derivative is equal to 0, and it changes from on top to the bottom at x equals -1. Again, your justification will be right here. The first derivative changes from positive to negative. Your relative min is when you're changing from negative to positive. So there's your minus sign, and there's your plus sign. You went from the negative portion to the positive portion as you're going from left to right. So that's going to be at x equals -3. Your justification is right here. Your f prime of x changes from negative to positive. All right, your inflection points. Now, inflection points are a little bit different. Inflection points are going to occur at relative maxes and mins on your graph. So our inflection points are going to be these fun little stars right here. So your inflection points are going to be at x equals -2, a +1, and a +2. -2, +1, +2. You might notice that at +2, it was in contention. It was a critical point. It could have been a relative max or a min of your function, but it wasn't because it didn't change places. It stayed negative and negative. So it didn't change from negative to a positive or a positive to a negative. It stayed negative, which made it an inflection point. Now, for the justification here, you're going to say it is a relative max or min on your derivative graph. Okay? That's your justification. You can't say the second derivative changed signs. The reason you can't say it is because you don't have the second derivative in order just to justify that. Okay? So you have to say it's a relative max or a min on the derivative, which is what it is that you have. Okay, so concave up and concave down. So concave up, that is going to be where you have positive tangent lines. And positive tangent lines are going to be where your function or your derivative is increasing. So we're going to go from -infinity to our inflection point, which is -2. And then we're going to go from 1 to 2 right here. Now, the justification is because the derivative graph is increasing. Now, you could say the slope of the tangent line of the first derivative is positive. That's just an awful lot of words. It's a perfectly fine justification. The slope of the tangent line is positive. It's just that f prime of x is increasing. It's just a little faster to say. Now, we're going to be concave down where we have negative tangent lines. Negative tangent slopes, I guess I should say. So we are from -2 to +1. And then again from 2 to infinity. And for this one, we are going to say that the first derivative is decreasing. And again, you could say the slope of your tangent line of the first derivative is negative, but that was a big mouthful. It was a lot to say. Any questions on number 9? Trust me, it takes longer to explain it than it does to actually do it. And once you've got it in your head and once you've got it all solidified, it goes much, much faster. All right, let's look at number 10, our last one. We are given an equation this time. F of x is equal to 2x cubed minus 12x squared plus 10. And we want to find all of those pieces, increasing, decreasing, concave up, concave down, all of that stuff. So essentially what I need to do here is I need to make a table like number 8. Once I have my table like number 8, I can answer all of my questions. So to make my table, I've got to find my first derivative or my critical points. So I'm going to pull out a 6x. I'm going to be left with x minus 4. So I get that x equals 0 and x equals 4. Those are my critical stationary points. Now I need to do the second derivative. And that is going to be 12x minus 24. I can pull out an a 12. But I only get a 2. Remember, this 12 doesn't have an x by it, so it's not going to create another x equals 0. Now, x equals 2 is my pip. It's my possible inflection point. So now I have all my pieces, I can make my table. Now, I haven't asked you to graph this thing. So since I haven't asked you to graph it, we don't care about the second derivative. We don't care about the function. We just care about the first derivative and the second derivative. So the first derivative, we're going to plug things into the first derivative equation. Okay. The first derivative, we had zeros at 0 and 4. The second derivative, we had a 0 at 2. So if I plug in a negative 1, and I have to plug into both pieces here, I have a negative times a negative. Well, that's a positive. If I plug in something between 0 and 4, it makes sense. I have a positive times a negative. That means that's a negative. And then over here, I plug in a 5. That's a positive times a positive. So I'm back to positive. So remember, this is increasing and decreasing. So then I know I'm increasing, decreasing, and then increasing again. Now I'm going to do the second derivative. And the second derivative I'm going to plug into this second derivative equation. Now again, I don't have to worry about the 12 because the 12 is just positive. I have to plug it into this x minus 2. So if I plug in something to the left of 2, 0, 1, negative something, it doesn't really matter. I get a negative value. If I plug in something to the right of 2, 3, 4, 5, I get a positive value. Now remember, this tells you concave up and concave down. So we're concave down here and we're concave up here. Now again, I am going to do all of our pieces of information, but I'm not going to go ahead and justify them because again, you can look back at number 8 for the justification. Okay? So we're going to be increasing from negative infinity to 0, and we're going to be increasing again from 4 to infinity, because the first derivative is greater than 0. We're going to be decreasing right here between 0 and 4, because the first derivative is less than 0. We have a relative max at x equals 0, because the first derivative changes from positive to negative. We have a relative min at x equals 4, because our first derivative changes from negative to positive. We have our inflection points, or point, at x equals 2, because the second derivative changes size. We are concave up from 2 to infinity, because the second derivative is positive. And we are concave down from negative infinity to 2, because the second derivative is negative, or less than 0. And that concludes number 10, and that concludes our practice problems. If you have any questions, please let me know. Have a great day.